Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 26, practice session number 8, in which we will solve our next problem, number 27. In the problem number 27, we are given a bounding generating circle named lowercase s and shown in white. And on that circle, 2 points, A and B, which must be distinct, are picked at random, and through these 2 points they're drawn a straight line named L and shown in red in such a way that that straight line L carries the chord AB of the generating or bounding circle S that partitions that circle into 2 complementary circular segments. The smaller one shown on top over here and the larger one shown on the bottom. This chord or the straight line L also partitions the circle itself into 2 complementary circular arcs, the smaller arc AB and the larger arc AB. Into one of these 2, doesn't really matter which ones, but into one of these 2 circular segments, they're inscribed a smaller circle named lowercase q, shown in yellow over here, and that circle is inscribed into the corresponding circular segment at random or at an arbitrary location. And that means that if, for example, the mathematical oracle picks at random the point D, which can occupy any legal position strictly inside the chord AB, then the location of the point C on the corresponding circular arc is fixed and non-negotiable, and conversely. If the mathematical oracle picks at random the point C on one of the complementary circular arcs, then for the corresponding circle Q to be inscribed into the respective circular segment, the position of the point D is fixed and is not negotiable, so either one of these 2 points is selected at random on the corresponding mathematical object, and let's say in accordance with that choice, the smallest circle Q is inscribed into the corresponding segment. And in that point, we're also given the point F, shown at the bottom of your screen in green, and this point F has the following property. This point sits precisely in the dead middle of the complementary circular arc AB, meaning the complementary in the sense that the point F is chosen on the arc that does not contain the point of tangency of the inscribed circle Q and the bounding generating circle S. And I captured this requirement over here, the circular arc AF. This portion over here by length is equal to the length of the circular arc BF, but we also understand that the minimizing geodesic distance-wise, the straight line BF or the line segment BF in length is equal to the length of the line segment AB. And the objective of this problem is shown over here, where to prove that the points C, D, and F, thus constructed and selected, are collinear. In other words, all these 3 points belong to one and the same straight line, which for demonstration purposes I named lambda, and that straight line is shown in green. And here is a short quiz for you in order to test your understanding of the problem statement. What do you think? How many degrees of freedom does this configuration of the input mathematical objects have? The correct response is that this particular problem has 5 degrees of freedom. The first degree of freedom is associated with the freedom of the inscribed circle Q to move freely within the chosen circular segment. Remember that The fact that the circle Q is inscribed into the corresponding circular segment arbitrarily means that that circle can be positioned anywhere within this segment. That's the freedom number one, degree of freedom number one. The second degree of freedom in this problem is associated with the freedom of the points A and B roam the periphery of the circle S in any which way, so long as the points A and B are distinct. The third degree of freedom is associated with this problem as follows. The radius of the bounding generating circle S is also free to change in any which way. In other words, into any circle based on any chord, we can have two complementary segments, and in one of these segments, the smaller circle Q can be inscribed. The fourth degree of freedom is associated with the freedom of the center of the bounding generating circle to roam freely the ambient plane. In other words, location-wise, the circle can be anywhere in the parent plane. And the fifth degree of freedom is associated with the freedom of the parent plane itself to take any possible position in the ambient or in the embedded 3 space. But in this particular problem, the last two degrees of freedom are of no interest to us, and the only degrees of freedom that are of interest to us are the first three degrees of freedom that I explained already. And in order to demonstrate visually how these degrees of freedom affect the configuration of the input mathematical objects, I have put together for you three animations using the free software GeoGebra, and here is one animation that showcases one degree of freedom in this problem. And here is the second animation that showcases 2 degrees of freedom of this problem. And here is another animation that showcases all 3 degrees of interest of this problem. Wonderful, we now understand that regardless of the position of the parent plane in the embedded 3 space, regardless of the location of the center of the bounding generating circle S, regardless of the radius of that circle can live and breathe in any which legal way, regardless of the position of the chord constructed based on such a circle, and regardless of the position of the inscribed circle Q, the claim of this problem or of this theorem seemingly remains true. The points of tangency of the inscribed circle with the corresponding chord and with the corresponding arc of the generating or bounding circle will be collinear with the point that sits in the dead middle of the complementary or opposite circular arc. This is what we are on a hook to prove. That's number one. Number two, whenever I look at anyone's animation or construction, I always wonder how was that animation or construction put together. And at this point, you should be wondering yourself, how did Roman put together this animation, or specifically, how did Roman inscribe the smaller circle Q into a given circular segment, given a randomly positioned point, let's say D on the chord, or randomly positioned point C on the circular arc. And at this point, I will be reflecting that question to you. How did Roman inscribe the circle Q into a given circular segment? And as a hint, you are equipped with all the tools and with all the knowledge in order to solve this problem on your own, specifically using the machinery of inversive geometry, which is the subject of study of this course. Now, this problem of inscribing the circle Q into the given circular segment based on a random point on the chord or a random point on the circular arc can be solved in a number of different ways, but pertinent to our case, one way to reason and one way to solve this little miniature sub-problem, let's say, is as follows. We know how to touch a circle with a straight line. This is an easy problem or a previously solved problem. This does not cause any difficulties for us, but touching the circle with a curved line, that is precisely a difficult task. We do not know how to do it. So how do we solve this problem? Well, with the childish naivete, we know how to inscribe a circle into the shape formed by two straight lines, for example, the line L and line lambda. If the mathematical oracle gives us two straight lines that intersect or which do not intersect, that's even easier. But if these two lines intersect, the mathematical oracle picks any one straight line, picks a point and says, here, inscribe the circle into this angle in such a way that the circle must touch this straight line, this side of the angle at this point. Well, this is a trivial problem. We know how to do it with Euclidean tools alone, a compass and a straight edge. So how do we solve the difficult problem? With the childish naivete, we say all we have to do is straighten out the curved line into a straight line, and then the problem is solved. So how do we uncurve a curved straight line? Well, we go back to our early theorems and recall that every circle that passes through the center of inversion is taken into what? Into a straight line that does not pass through that center of inversion. And what do we do in this case? Well, we pick either the point A or the point B. It doesn't really matter. We make either one of these points the center of inversion, pick a non-zero radius, and then the straight line L will pass through the center of inversion, the point A or the point B. It will be taken into itself. Let's say with positive power, we flip the corresponding bounding generating circle into what? Into a straight line that doesn't pass through the center of inversion, but it doesn't really matter. We now have two straight lines. We reflect the point, let's say if we're given the point D, then on the arc we reflect the point 2. That point will be somewhere on the straight line L, and then we inscribe a circle into the shape that is delineated by two straight lines that touches the line L at the image point D prime, and then we reflect the whole thing back, and voila, we have our circle Q that is inscribed into a given circular segment. That is number 2. This is a small problem. I do not branch it out into a standalone problem, I think, and I hope that all of our viewers are indoctrinated and already mature enough to solve this problem on their own and their own time. You do not need me to tell you to do that. And the third point is the following. It may sound like a beat up cliche, but it is the case that, let's say, no good painting is ever complete or completely done. It just walked away at an opportune moment. No good book is completely done or complete. It just walked away at an opportune moment. Likewise, by analogy, no good sculpture is ever complete. It's just walked away from at an opportune moment. And finally, is pertinent to us, no good mathematical problem that is designed to teach a student how to think like a mathematician is ever completely done. It is just walked away from at an opportune moment. And unfortunately, in, let's say, the setup of a middle school or a high school lesson, or a session at a math circle, or even in a more general setting of a college lecture or a college seminar. All these discussions are cut short by, that's right, by a bell, and any such worthy or interesting correct mathematical problem that is designed to teach a student how to think like a mathematician can be investigated in a number of ways listed over here on the right side of your screen. In other words, in that context, it is possible to discuss the specific details of a specific proof that was already put together. It is possible to discuss a multitude of tactical approaches that can be used in order to generate a proof or solve a problem. It is possible to discuss the points of tangency and points of intersection, if there are any, across the multitude of tactical approaches. It is possible to discuss or embed the solution or a proof into a more fundamental look at the problem-solving approaches that were able to crack that theorem or crack the solution of the problem. This is actually what we did in our practice session, where we discussed how the verbal math college entrance examinations may work, where when we solve a particular problem. It is also possible to discuss the possible generalizations of a theorem or of a problem, and here these generalizations can run in a multitude of directions. This is a small universe of its own in mathematics, generalizing a given problem, because there are many dimensions over which a generalization can be made. We can increase the number of summands, we can increase the number of factors, we can try to change the quality of the objects that we work with. For example, if we solve the problem with the square, maybe we can try to solve a similar problem with the cube, or we can take a circle into a sphere, and so on. It is also possible to discuss the offspring theorems and problems that are in a way birthed by this theorem or by this problem. And it is also possible to discuss the role of this or that theorem when it is embedded into the larger fabric and the larger landscape of mathematics, and on and on and on. These discussions are rarely carried out precisely because of the bell, and there's simply not enough time to cover all these points. Consequently, the emphasis of this episode will be on the importance of studying the proofs of the theorems in any area of mathematics, not necessarily in inversive geometry. George Poya, the author of the immortal How to Solve It book, which is basically a must-read for any person who wants to deal with exact sciences, mathematics, physics, or computer science, it doesn't really matter, used to say that we begin generating or we begin proving a theorem only after we understand why this theorem must be true. So when we cast our eyes on a given problem, we think why this theorem must be true. Let's try to think about this together. We are given how many points in this problem? In this problem, we're given 5 points. A1, B2, C3, D4, and F5. Do all these 5 points have one and the same quality? Well, the answer is no. All these 5 points do not have the same quality, because amongst these 5 points, the first 4 are completely random. In the animations that we just saw, the points A and B can be positioned in any which way. The points C and D can be positioned in any which way as well. That is why we say that within, of course, legal boundaries of this problem, the first 4 points, A, B, C, and D, are completely random. But the point F is not random at all. The point F has how many? 3 very specific properties. First of all, the point F is fixed. That's one property that's quite interesting about the point F, because regardless of the position or orientation, if you will, or the size of the chord AB, the point F will be always located in one and the same spot. It will be the dead middle of the corresponding complementary or the opposite chord AB of the generating circle S. That's the property number 1. That's interesting about this point. The property number 2, or the characteristic number 2, that is interesting about this point, and that is not random at all, is that the point F, out of all the points in the ambient plane, is located specifically on the circle S. It is not located in the circle S. It's not located outside of the circle S. It is located exactly on the circle S. So that's two interesting characteristics, or two interesting properties of the point F. And the third interesting property of the point F is that apparently this point F, or so we are told by the author or authors of this problem, is that the point F is the dead middle of the corresponding arc. So fixed on the circle and in the middle of the arc. Three interesting things. So how do we wrap our brain around this particular situation? Well, here's one thing that we can do in this case that is popular anywhere else, actually, in mathematics, not only in geometry, but literally any other area of mathematics you can think of: real analysis, complex analysis, theory of groups, theory of numbers, theory of graphs, and on and on and on, integral equations, differential equations. All these areas have this maneuver in its chest of tools. What we do over here is that we temporarily remove the specificity in this situation, and we try to take this randomness and construct the following implication: if random, 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 then not so random. So in other words, if we temporarily remove the point F from our picture and try to deal with 4 random points, then how can we hone in, or how can we hit upon the point F that has all these 3 properties that we just discussed? In other words, if we throw out the point F temporarily, let's say we have our circle, we have our chord, we have our point A, we have our point B, we somehow have our circle Q inscribed, this is our point D, this is our point C. In this configuration of the input mathematical objects, how does the point F come into existence, and this way in which it comes into existence, how does it explain its properties? Well, look at this. We have 2 distinct points, C and D. These 2 points define a unique straight line no matter what. So if we construct this straight line through these 2 points, this straight line will run on and on and on. This straight line, any straight line, can intersect a quadratic curve only at most in 2 places. One such place will be the point C, and the other such place will be the point we will designate it as the point X. What properties does the point X have, or for that matter, what properties does the straight line CDX have? See, this is our analog. The straight line CDX is the analog of the straight line lambda, except that in this problem we're given the properties of the point F. We're told that this is the dead middle of the opposite circular arc. Here we do not make this statement, we do not take it as a given, we simply synthesize the problem X by constructing a straight line that passes through the points C and D, and now we're trying to deduce what properties does it have. Well, let's think about this together. Whenever we have 2 circles, the one fact that sits in the back of our mind at all times is that all circles are homothetically similar. In other words, if we're given 2 circles, there always exists the homothenity of the parent plane, whether it will be uniform expansion or uniform contraction with a positive coefficient or negative coefficient that will take one of the circles into another. If these circles, and depending on the location in general, actually there are 2 centers of homotheity that will take one circle into another. One center will take one circle into another with negative coefficient, the other one with positive. So here we have 2 points, 1 point, and we have 2 circles, Q and S that share a common point at C. What does that mean? That means that if we consider the homotopy of the parent plane centered at the point C with the coefficient K that is equal to, let's say, the radius of the circle S divided by the radius of the circle Q. Here, the radius of the circle S as a real number is strictly larger than the radius of the circle Q as another real number. So this coefficient is positive and it is greater than 1. And what that means is that the homotopy of the parent plane centered at the point C with the coefficient K will be a uniform expansion of the parent plane that, intuitively speaking, will blow up circle Q into the circle S. And here is two theorems that pretty much you will prove yourself as soon as you begin studying the geometric transformation of homotopy. Homotopy will take any straight line that passes through the center of that homotopy, like for example this straight line, into itself. So this straight line will be taken into itself by the homotopy. Let's record it this way. Homotopy with the center at the point C and with the coefficient K. It will take the straight line CD into itself. Wonderful. The next theorem that you will prove as soon as you will begin studying the transformation of homotopy is the following. Any straight line that does not pass through the center of homotopy, just like the straight line L, will be taken into a straight line that is parallel to the original. In other words, the straight line L, when the parent plane uniformly expands, the point D will be taken into the point X. So the point D will go into the point X, and the straight line L will be taken into what? What role does the straight line L play with respect to the circle Q? It's a tangent to the circle Q at the point D. This is our definition of what does it mean to inscribe a circle Q into the corresponding circular segment. So the straight line L will be taken into a straight line that will be parallel to the original L, and it will also be what? It will also be tangent. This straight line tau will be tangent to the circle S at the point X. And here we can reason in a number of ways. Look at this. What favorable things we can do already here? Well, look at this. We have two parallel straight lines, L and tau. And without any circles, what good things can happen over here? Well, that's Euclid's Elements book number 1. If a straight line such as the straight line BX falls on two parallel straight lines, then that falling straight line makes the magnitudes of the corresponding angle equal one another. In other words, this angle right here, let me use maybe red so you can see better. This angle right here will be equal to this angle. You see, this is a trivial observation. Straight line BX falling in two parallel straight lines, tau and L. Now we go back to the theory of circles, Euclid's Elements, book 3, proposition 31. What is this proposition? This is the theorem from the theory of circles that establishes a relationship across the angles that are formed by the tangent to the circle and an arbitrary arc or arbitrary chord that is drawn through the point of tangency. This is the alternate segments theorem, if you will. And according to this theorem, what interesting statement or favorable statement we can make over here. Look at this. This angle right here will be the same angle under which this chord BX is seen anywhere from anywhere on the corresponding arc of the circle. In other words, this angle right here, let's say CB, what will it be? Well, this angle right here will be exactly the same color, you see, by book 3, proposition 31, the alternate segments, the angles in the alternate segments, this angle is equal to this angle. And what else can we say, what other favorable conclusion can we make over here? Well, look at this. Our angle, if you will, dBx, this angle, extended into angle ABX, subtends which arc? It subtends this arc right here. So the angle ABX stands on this arc right here, this or this arc. And by the corresponding theorem from the theory of circles, what else can we say? Well, apparently the magnitude of this angle, as long as its vertex is located anywhere on the same side with respect to the chord or to the arc, will be the same. What other interesting angle in this case subtends the same arc AX? Well, this is this angle right here. This is the angle ACX. It is the same angle. See? This is exactly the same angle. Why? Because both of these angles subtend this arc. And what did we just prove? Well, effectively we proved that this angle is equal to this angle, and that means that in this setup, forgetting about the point X, out of randomness of the points A, C, D, and B, there comes not a randomness, but an if P then Q implication that is non-negotiable. There is no room for negotiations for the point X. The line segment, if you will, CD, or any straight line that passes through CD, will play the role of what? Of the bisector of the angle ACB. And if it's extended, it will run into a point X. It will be on the circle. And what other property of the point X, the final property of the point X that we can deduce from here? Well, look at this. We have one angle over here at the vertex B set to a certain magnitude. And we have our triangle AXB. If we can prove that this angle right here is the same as this, then the corresponding triangle will be isosceles. So the distance XA will be the distance XB. Correspondingly, the point X will sit exactly in the dead middle of the arc log B. How can we do that? Well, let's take a look at this situation right here. Let's concentrate on the magnitude of this angle, XCB. This angle stands on this here arc, or a chord, if you will. What other interesting angle stands on the same arc or chord? Well, exactly this angle, XAB. Look at this. This guy stands on the same arc or the same chord, and it's located on the same side with respect to that chord, this vertex or this vertex. So now we have a triangle AXB, the magnitude of the interior angles of which at the base AB is one and the same. This here angle is equal to this here angle. Such a triangle is called isosceles, and in an isosceles triangle we have this side by length equal to this side. So these sides represent the so-called minimizing geodesic for the given space, Euclidean plane. This geodesic is straight line, bam, bam. But that also means that by length, the arc BX is equal to the length of the arc AX. And now we can say that by defining our point X is the point F in our original problem. So now we generated a very straightforward proof of the following properties of the point X. This point X will be fixed if our chord AB somehow lives and breathes, let's say moves, executes or exercises its degree of freedom of moving about the generating circle S. Its middle will always be in one and the same spot. It doesn't really matter. So the point X will be fixed. It will be, that's number one. Number two, evidently it will be on the circle S. And number three, it will be sitting in the dead middle of this arc. And now that we understand why this theorem should really be true, because now let's go carefully to the if p then q implications. Here we took the randomness of the 4 points a, b, c, d. If random this, then this follows. And in some sense we turned our problem over here inside out, if you will. We took it as the fact that the point x and the point c and d are collinear, because we simply snapped the straight line, took the point x, so the point c dx are collinear, or in some sense the point c df are collinear. This is a given, and from that given, if p then q, we deduce the fact that this must be the case. In this problem, we need to do the converse statement. Here we're told that the point f is a dead middle. So here we're given the conclusion of this problem. If random, then the middle. But here we're told if the middle, then collinear. So now we understand that, yes, this theorem that we are asked to prove in the problem 27 is really true, and we can begin thinking about how to construct the requested proof. And now we can move on to the meat and potatoes of this episode and get a glimpse at why it is important to study the proofs in any mathematical layer. It doesn't have to be inversive geometry, like I said again. It could be the theory of groups, theory of numbers, theory of graphs, differential equations, integral equations, real analysis, complex analysis, topology, and on and on and on. And there is no need to memorize all this proof. This is a futile exercise, but there is a need to capture the gist of a proof. And once you start capturing or attempting to capture a gist of a proof, you want to compress it into a very small number of words that carry the technical essence of this proof. Then inevitably you will begin coming up with the so-called heuristic templates. And this was my pet. This is why I dedicated season 1 and season 2 on this channel to the description of these heuristic templates, which otherwise are known as, let's say, problem-solving approaches: transform and conquer, reduce and conquer, expand and conquer, reverse order, space-time equation, and on and on and on. So in this specific problem, why was it important to study all the proofs, aside from trying to understand the essence of whatever material we cover? Well, if you were able to, we zoom in here on the theorem number 10, if you were able to generate the proof of this theorem on your own that was relevant and correct, this is very good. You should have no problem with what is about to transpire. And if you did not, but you worked your way through, you honestly went through this proof and understood what is going on, how this proof was put together, then this is precisely what we bring into the problem number 27. We pull up in our mental image, we pull up the diagram that we generated for the proof of the theorem number 10. And again, as a friendly reminder, what did this theorem say? Any straight line that does not pass through the center of inversion O and has precisely two distinct points in common with that circle, we name these points F1 and F2, such a straight line L under the inversion of the parent plane with respect to the circle C. Circle C centered at the point O will be taken into a circle that passes through the center of inversion and precisely through the shared points F1 and F2. And how did we prove? What was the technical essence? What were the details of that proof? Well, the details of the proof were the following. We proved that the triangles in this case that we carefully select must be similar. And then in similar triangles, all the angles, the corresponding angles must be similar. So if our original triangle was right, then its similar triangle, similar cousin must also be right. And it must be right in such a way that certain distance from the center of inversion to the image of this point that sits on the input straight line, since this distance is fixed and this angle is right, then the only orbit of the point F or of this point can only be a circle that precisely passes through the center of inversion, because this diameter on which these right triangles are built precisely is terminated on one side by the center of inversion. That was our line of reasoning. And once we do that, we also automatically recall, I will reflect it, let's say in yellow. What was the converse of theorem number 10? It was the theorem number 15. Look it up in your records. You will see that in this theorem, we prove that if a circle, the input circle Q, passes through the center of inversion and has precisely 2 points in common, F1 and F2, two distinct points in common with the circle of inversion C. I show it in lightly, very lightly in white. Hopefully you guys can see it. If you want me to press harder, let me know. Then such a circle will be taken exactly into a straight line that does not pass through the center of inversion, but passes precisely through the shared points F1 and F2. And we actually, if you go back to your records and pull up the corresponding chapter from my free book, Inversive Geometry for All, you will see that I even put together for you a template that can be used to generate all the relevant theorems that deal with circles that are taken into either straight lines or circles. And that template basically mounted again on the same thing. We take a point on the circle, we reflect it into a certain point, and then we prove that the corresponding triangles must be right. So the only choice for the orbit of the image of such a point, random point, will be such a locus of points in the parent plane such that this angle right here must be right. That means that this orbit must be straight line. And we remember we proved the similarity of these triangles by using what? The workhorse, the algebraic embodiment of inversion. Distance times distance is equal to the square of the radius of inversion. That was the technical essence. So once we have all these details in the upper crust of our brain, 10:15, we have the mental image. We're in command of this material. We understand how we generated this proof. Now we basically take this proof and lift and shift. We'll lift it and we shift it to the left, and boom, we drop it on top of our problem 27 at hand. So what can we say when we juxtapose these two diagrams? What can we say? Well, we can establish a certain correlation. Look at this. In this case, this is some degree of freedom over here, but let's say our point A in this problem, our point A corresponds to the point F1 in the theorems 10 and 15. The point B corresponds to the point F. In other words, our shared points A and B corresponds to the shared points F1 and F2. What else? The point F corresponds to the point O. Look at this. The point F corresponds to the point O. What else? Well, we have our bounding generating circle S that passes through these 2 points A and B corresponds to what? Our bounding circle S corresponds to the circle Q in this case. And our straight line L in the given problem corresponds nicely to, so L in our problem corresponds to L in these two theorems. So now we beginning to catch the similarity between two configurations. And how did we hone in on these configurations again? How did we hone in? Being detectives, let's say we're playing the math detective, the Sherlock Holmes of mathematics, if you will. How did we hone in on this thing? Well, because precisely of the importance of studying the proofs in any given layer of mathematics, including but not limited to inversive geometry. So because we're in control, we're in command, we studied this proof. Sometimes we actually can generate such proofs. We were able to yank that material from our web of mathematical knowledge and schlep it onto the problem at hand. So we have it. Now we think, what is one object that is present in both of these theorems is missing over here in our problem? Well, that object in this case is a rather specific circle of inversion C. We have it here. It's one of the central characters of both of these theorems, 10 and 15, but so far it's missing over here. So this is the next step when we solve a problem in mathematics, just like a problem in theoretical physics or computer science. There are no guarantees of any kind. We do not know a priori or ahead of time if our current step will lead to success. The only choice we have is to try. So here We can try this next maneuver, but we understand why we expect this maneuver to work, or we think there are good reasons or good chances that it will work. Because these things worked in these two theorems which we studied and generated the proofs of. So now we take and our point F that we were given and we make it the center of inversion. In other words, we introduced the circle of inversion, lowercase c. I showed it again. I did not want to stress it and emphasize it too much. This is where it is. If you guys cannot see it too well, I apologize. But again, I do not want to pollute the drawing more than I have to. In some sense, if you solve enough of problems, you do not really need to draw the circle of inversion. All you have to know is that F is the center of inversion. Let's write it down over here. Our circle of inversion will be centered at the point F. And what will be the radius of inversion in this case? What do you think are the good candidates? Well, again, by analogy, we come to our theorems 10 and 15, and what do we see? What is the radius of inversion? Well, in this case, it's a side effect, of course, of these particular theorems, the way they are worded, but the radius of the circle of inversion over here is the distance from the center of inversion to the shared points, because the shared points belong to multiple geometric objects at the same time. They belong to the circle of inversion, the straight line L, and its image Q, or conversely, the pre-image Q and its image L, when the power of inversion is positive. So here we do the same thing. We take the distance BF or AF to be our, so it will be AF or BF, it doesn't really matter, to be the center of inversion. This is it. And now we try. Remember, this is also somewhat softly templatizable step. The tidal wave of inversions, which objects will be taken into which objects under the chosen inversion. Let's do this together. The points A and B will remain fixed. So here we now keep our doodling aside, and now here is serious business. So under the inversion with positive power, so our radius of inversion will be, let's say, AF squared with a plus sign, positive power. The composition, there is no composition, one inversion, one is enough. So under this inversion of the parent plane, all these objects will be taken where? Well, let's see, the point A will remain fixed. It will be taken into the point A. The point B will remain fixed. It will be taken into the point B. You see, these points, they belong to the circle of inversion. They remain fixed. What else can we say? Well, let's say our input is the straight line L. The straight line L will be taken, look at this, L into Q, but in our case, Q is S. So the straight line L will be taken into the circle S, and conversely, the circle S will be taken into the straight line L. This is the beautiful part. So both ways, we put the arrow, it works both ways. Now, what else can we say about the interesting objects in this case? Well, let's look at the points D and C. Points D and C are located in such a way that, let's say, the point D is located on, let's say, pre-image straight line L. C is located on the image of L, circle S, or conversely, the pre-image point C located on the pre-image circle S is located on the located at the image point of this D on the image L. So now C is taken into D, and D is taken into C, uppercase C, as points, not to be confused with the name of the circle of inversion. The point C is taken into point D, the point D is taken into point C. This is exactly the mechanics of our, remember, this is the mechanics of the proof of the theorems 10 and 15. This is precisely how we generated the proof. So this is all nice and comfortable. We feel that we are onto something over here. So now we bring in, what else is missing over here? Well, this mysterious straight line lambda, we did not say anything about it yet. Let's deal with this guy, the inscribed circle Q. Look at this. The circle Q, by definition, must pass through the point D, through the point C. So here we recall what, let me use yellow again, the theorem number 39, if I'm not mistaken. According to the theorem number 39, the circle, any circle that passes through 2 points, such as the points D and C, that are the inversive images of each other under a certain inversion, remains what? The circle Q remains orthogonal to the circle of inversion C. Remember that. This is based on the, let me this time write it down in red a little bit here. This is theorem 39. The circle Q passes through the points D and C. The points D and C are the inverses of each other under the inversion of the parent plane with respect to the circle, positive power, blah, blah, blah. It means that this circle Q is orthogonal to the circle of inversion C. And what is the next theorem that we bring in? The next one, if I'm not mistaken, again, it's 41. Keep me honest, verify. But according to the theorem number 41, any two circles that form an orthogonal pair, according to the theorem number 31, let's say if circle X is orthogonal to the circle Y, then any one of these circles will remain invariant under the inversion of the parent plane with respect to the remaining circle. And what does that mean? Look at this, how beautifully these things play out. That means that according to our chain of theorems, the circle Q will remain invariant under the inversion that was chosen. That means that the circle Q will be taken into itself. So now let's look at this amazing, absolutely amazing situation. We managed to find a geometric transformation under which all the material in somehow is shaken but not stirred and remains where it is. In other words, as the geometric object, collection of geometric objects, they all remain where they are. Yes, the straight line L is taken into the circle S, but at the same time, the circle S, as L is taken into S, S is taken back into L. So all our objects, amazingly enough, remain fixed. So this is a tactical victory that we were able to score precisely because we studied the proofs in the layer of mathematics known as inversive geometry. Now, what does it mean? Well, the final step of our proof is the following. According to, if I'm not mistaken, definition 2, remember we defined positive power of inversion when the image points, the image and pre-image points sit on the same side of the center of inversion. And indeed, the points D and C over here are located on the same center of inversion. That's definition 2. And then in definition 1, you will have to look it up. I forget myself what was the condition. I think it was the condition number 2, if I'm not mistaken. The points, remember that how we define the geometric transformation of inversion. It's the transformation under which the pre-image and image points remain collinear with what? With the center of inversion. The center of inversion in this case, what was the point F? And that precisely means, that the points C, D, and F belong to one and the same straight line. These points, C, D, and F, must be collinear. And here, maybe I did not explicitly say these words, that the point F is equidistant from the points A and B. Well, look at this. In our theorems 10 and 15, what can you say about the point O, the center of inversion, and the points F1 and F2? Well, they are equidistant from the center of inversion, and in some sense, these points sit on the perpendicular bisector of the corresponding chord, F1, F2. So Here is the direct analogy, and these words are said, and this completes the proof. We now prove that the points C, D, F under the given conditions are collinear. They belong to one straight line. But this is not it. Remember one of the points that you saw several seconds ago when I said that there's a lot of things to discuss when we solve this or that technical problem, and usually we do not have enough time. We're cut short by the bell. But in this case, we have a little bit of time, so we can take on one point over here when I highlight it for you, and that is the discussion of how the given problem can be generalized. Elsewhere on this channel, I already mentioned this is as my personal opinion that it is difficult to, or quite challenging to come up with one single crisp definition of generalization of a problem in mathematics in such a way that all the mathematicians in the room will agree on it, simply because a generalization of any given worthy, interesting mathematical problem can run in multiple directions or in multiple dimensions, if you will. We can increase the number of summands, increase the number of factors. We can change the quality of the underlying object. For example, instead of a square, we can try to deal with the cube. Instead of a circle, we can try to deal with a sphere. For example, in our case, is it possible to assume that what we are witnessing over here on the plane is basically cross-section of a three-dimensional situation where S is actually bounding generating sphere, Q is also a sphere, the straight line L is basically a plane that cuts the generating sphere S. We have a spherical cap, if you will. Into that cap we jam another ball, if you will, and this ball touches the cap, touches the plane. Straight line, will it run into the South Pole of that sphere, yes or no? That's one way to generalize a given mathematical problem. When we deal, for example, with integrals, we can introduce a parameter that will scale an interesting variable in some way. Then we can differentiate over that parameter, integrate, and on and on. So it's not really clear what does it mean as a one crisp definition, generalization of a problem. What is it? But in this case, we will concentrate on a topological generalization, and the topological generalization means the following. Over the course of the proofs of the theorem, starting from the theorem number 1, taking it all the way up to theorem, I forget, 30 something, we basically prove that topologically straight lines, and circles are topologically equivalent. And that means that this topological equivalence is established in the following sense. Any straight line that does not pass through the center of inversion is taken into a circle that does pass through the center of inversion, and conversely, any circle that does pass through the center of inversion is taken into a straight line that does not pass through the center of inversion. And earlier on, remember, we equipped our Euclidean plane with the point at infinity. We thus obtained an extended plane. The same maneuver is carried out in complex analysis when the complex plane is extended with the point at infinity. But with this extended plane, now our mapping of the parent plane into itself became a bijection. So the combination of these two things, a bijection and the topological equivalence of straight lines and circles, in the sense that I explained, in the specific sense that I explained, straight lines not through the center flip into circles, circles through the center flip into lines that do not pass through the center of inversion, we can generalize our problem as follows. Let's think about this straight line over here, L. What is it? Well, in the light of topological equivalence of straight lines and circles, we can think of the straight line as of a circle. What type of circle? Well, that's a circle whose center was taken into the set point at infinity, which extends our finite real plane. So in this case, the straight line L becomes a circle. So then let me keep this drawing as it is. I will hijack the drawing on your right. let's say we flipped our straight line L into a circle due to the equivalence, topological equivalence of circles and straight lines in a specific sense. And then let's say we trapped, where's my yellow? We trapped, so now let's say this straight line became a circular arc over here relevant to us. So now we have a circular arc. Forget about the circle of inversion for a moment. I'll just hijack the same straight line to keep the number of objects minimal. And pretend that this straight line is sort of gone. This is gone, this is gone, this is gone, this is gone. Forget about the theorem. We're simply hijacking the drawing. So now, if we do the same maneuver to this configuration over here, now this object over here trapped between two arcs, two circular arcs, this object over here has a separate name in mathematics. It's called a loon. I think that's what it's called, a loon. And into such a loon, we will also inscribe circles Q in the same way. So we inscribe the circle Q in the same way like this. See? This way, or this way. Then what are we expecting to happen in this case? Well, it turns out that in this case, the points of tangency of such an inscribed circle, they will all pass through a fixed point. Over here, I will use the same designation for this point F. That will be equidistant from the points that define or delineate or participate in the formation of the loon. And why do we think that this theorem is true? How can we prove it? Well, without the machinery of inversion, by using pure elementary means that are based, let's say, on nothing but the naked Euclid's elements, it is actually quite challenging to prove that fact, that as the circles are inscribed into such a loon, their point of tangencies define a straight line that will always pass through one and the same fixed point, regardless of where that circle is located within the loon. But with our machinery that is available to us, the bijection plus the topological equivalence, it becomes a child's play. Look at this. The way we can do it, the way we can prove that this theorem is also true, or a topological generalization of our straight line theorem is true, we can do it by executing the following maneuver that's popular elsewhere in mathematics also. We pretend that this configuration is the output configuration. And the output of what? Well, it's an output of some other configuration plus some other transformation that was applied to this mystery configuration in such a way that we were not in the room when the mystery configuration X was married with the mystery transformation Y. Once a happy marriage happened, the output was produced, this drawing, this configuration right here, then we will let into the room, and voila, we have the beginning of our episode, given the bounding generating circle S and the port L, and so on. So what was this mystery configuration and what was the mystery transformation? Well, it is not that difficult to manufacture precisely what we have over here. Let's say, which color did we use? Okay, so let's say we have a circle. We have the circle S prime, and we have a circle that intersects the circle S prime, and that circle is called, which one did we call it? Let's say we will call it L prime. You see, we have two intersecting circles. That's the mystery initial configuration. In such a configuration, there always will be two distinct points, one and the other. And these two distinct points will define a straight line. These two circles will have their centers somewhere. So the line of centers will always intersect one of these circles at an interesting location. It doesn't really matter which one we pick. We can pick S prime. We can pick the circle L prime, it doesn't matter. Let's say we pick this circle, the point where the line of centers intersects the circle L prime for the second time. We make this point right here the center of inversion, and then we take our circle of inversion to pass somehow to be exactly this. This is the radius of inversion. So the circle of inversion will somehow pass, this will be our circle of inversion. Then we flip the parent plane with respect to this circle centered over here with this radius. The circle L prime will be taken precisely into this straight line, and that straight line will be called L. This is our straight line L. And the original circle S prime will be taken into some, let me use a different color, will be taken into some other circle. So with this guy, well, it will be jammed in somehow in an interesting way, but let's say, pretending, this is not very realistic, but let's pretend. So this will be our circle. Voila, we have our problem. S is the circle shown over here, straight line L is shown over here, and into this here space we jam in our circles between the dark green circle S and the red straight line. See right here, we inject our circles right here. This is our problem. In other words, we took our mysterious or mystery configuration of two intersecting circles. We introduced an inversion that flipped precisely a circle into a straight line, a circle into a circle, and voila, we have our straight line, quote unquote, straight line problem that we're given in problem 27. But because of bijection and topological equivalence, that precisely means that we execute the reverse transformation and flip the straight line problem into its original. We'll have precisely the straight line L will be taken into the circle L prime. The circle S will be taken into the circle S prime. We will have this configuration. We'll have a loon, two circles intersecting. We'll have a loon, and inside that loon they will sit. These circles will be taken into the circles that are inscribed into the loon. This one right here, see this guy, that is trapped between the circle S prime and L prime here. So each one of these yellow circles, our circles Q, they will be taken into the circles that are inscribed in the loon. And that is exactly true. This is how we prove this much more elaborate from the elementary geometry standpoint theorem. It is true, and mechanically, or with the hat on that says a physicist in terms of physics a little bit, we can even formulate the following theorem. If we pretend that the circle Q oscillates in a given, let's say, fixed loon shown over here, then it will oscillate in that loon in such a way that the straight line through the points of tangency of this oscillating circle with the bounding or generating arcs of the circles will always pass through a fixed point. And in order to show you that this is true, again, how many degrees of freedom there will be in this problem, in a much more difficult problem where both bounding curves are real genuine curves, not a straight line and our circular arc, but two circular arcs. Well, the 1 degree of freedom for the oscillating circle that we can pretend it's some sort of pendulum, mathematical pendulum that swings back and forth and changes its not only position but its size. That's 1 degree of freedom. Then we can have the degree of freedom, another degree of freedom for the points F1, F2 to behave in some way with respect to any one of the circles actually. Then we can change the radius of the outer circle, inner circle, and so we can count carefully if we care to how many degrees of freedom that this problem will have. But in the animation that you're about to see that I put together for you using the free software called GeoGebra, I only exercised 1 degree of freedom, and in that animation you will see how the circle Q will run back and forth in the loon that is formed by two circles, and the points of tangency of this oscillating circle trapped between two circular arcs will always pass through a point that remains fixed at all times. As a recap, in order to make sure that we do not miss the forest for the trees, using the theorem that we proved in this problem 27 as a stepping stone, we proved a more interesting and more challenging theorem according to which if a circle Q oscillates between two circular arcs in a loop in such a way that it remains tangent to the bounding circular arcs, then the points of tangency of the circle Q with the bounding circular arcs will define a straight line that will always pass through a point that is fixed, and that point evidently is equidistant from the points that define the said loop. Now, this is it for this episode and for this problem. And as a friendly heads up, as a fair warning, in the next practice session, we will be solving the following problem. We'll be given a circle, a certain circle, and then we'll be given 2 points, and then we will have to construct a circle that passes through these 2 points, but then it intersects the original given circle under a given angle that is given ahead of time.